Students, welcome back. Myself, Dr. Shashidhar, demonstrating one of the optical experiment called Newton's rings for you. This video is recorded by Professor Nityanand Chaudhary. Now we shall discuss the theory as well as working of the experiments in detail. Okay. Right. Now listen here. What you can see here, look at this. This is your plane of convex lens, correct? So we are discussing Newton's rings now. So now from where you get rings, just see this. This is the plane of convex lens. So what we are doing is we are estimating the radius of curvature of this plane of convex lens, right? So using this method called Newton's rings method. So now to understand this working, right, let me explain the parts of this setup. What you can see here is a plane of convex lens. Below this you have a glass plate, correct? So between plane of convex lens and the glass plate there is air here, right? There is air, right? Now here you can see a monochromatic source. You can see a monochromatic source here. So when light from monochromatic source falls on the lens, so what will happen? You get parallel rays, correct? So parallel rays. So these parallel rays fall on the glass plate kept at an angle of 45 degree. So then what will happen, as this light hits the reflector, right, it gets reflected, it goes down, right? As it goes down here at this point, right, you can see this curved part, some part get reflected, right? So some part get reflected, this is the reflected part. The other part pass through air here and falls on the upper edge of the lower glass plate. This is the upper edge of the lower glass plate, right? So if the path difference between these two rays, if it is n lambda, you get bright rings. You can see here, you can see bright and dark rings here now, right? So if the path difference between these two rays, if it is between these two, if it is n lambda, brightness, otherwise if it is 2n plus 1 into lambda by 2, it is darkness, right? So the overall experiment works on the principle of interference, right? So what is interference? Modification in the distribution of light energy due to the superposition of two or more waves. Here superposition of these two waves take place now. As a result you get the interference pattern, right? Okay, now the question is, why you are getting circular rings only, correct? Now, so why it is circular? Because see this is the point of contact, this is the point of contact. Around the point of contact there is air which is symmetrical, right? Since the locus of all points around the point of contact is symmetrical, right? So you are getting a circular rings, correct? Okay, then at the point of contact here, at the point of contact, so what you can see is there is a dark ring, correct? Why? Because at the point of contact here, the effective path difference is, you know, the effective path difference is 2 mu t cos r minus lambda by 2. If effective path difference is n lambda, you get brightness. 2n plus 1 into lambda by 2, it is darkness. So since the thickness of air film at the point of contact, since it is 0, you get the effective path difference in terms of lambda by 2. Since it is lambda by 2, you get darkening at the point of contact, right? So all these rings is visible with the help of this microscope. So when you place microscope above this setup now, this glass plate, plane of convex lens and the glass plate, this is the plane of convex lens, this is the lower glass plate. So when you place this setup below the microscope, I can see the ring system. This left hand side you can see this picture now. So this is the microscope, right? This is from which through this I can see the image. So here you can see a reflector, right? So below the reflector, somewhere here there is a plane of convex lens and a glass plate. Somewhere here there is a light source. So from light, this from sodium light source, light hits the reflector, then it goes down, correct? So this is what you can see here. So light hits the reflector, then goes down. So then between the plane of convex lens and the glass plate, interference takes place. Because of interference, you are getting the ring pattern, right? Now we shall move further. Okay, right. Okay, now you look at this. In this, here you can see a plane of convex lens. This is the glass plate. As light hits the curved surface, right? So this is the curved surface now. right? So some part get reflected, right? Some part get reflected. Rest pass through air, pass on the lower, pass on the upper edge of the lower glass plate, get reflected, right? So then it goes up. So these two rays interfere. Okay, if they interfere constructively, bright rings you get. If they interfere destructively, you get dark ring, right? Okay. Now, right. Next, you see here. Now, whenever light travels, look at this. Whenever light travels from a medium of one refractive index to the other, what will happen? Right. So you can see here, the light is traveling from air, that is one medium, to the other medium. Correct? No. So somewhere here it gets reflected. Correct? It gets reflected. Next, we'll move. Just see this. Then what is you can see in the right side diagram is a flat glass plate, correct? Flat glass plate. Above that there is a plano convex lens. Between plano convex lens and a glass plate, there is air, correct? Now there is air. So between this curved surface and the plain glass plate, okay, multiple reflection take place. So because of multiple reflection, because of interference, you are getting the ring pattern, right? Okay, now you know why you are getting rings, circular rings, because around the point of contact, thickness of the air film is uniform. Hence, you are getting bright and dark circular rings, correct? So they are named as Newton's rings, correct? And then I said, if the path difference between these two rays, if it is n lambda brightness, if it is lambda by 2, just it is, if the path difference is lambda by 2, darkness. So depending on the path difference, you may get brightness or darkness, right? Okay, this method was proposed by Isaac Newton, hence the name Newton's rings. Okay, next we'll move further. Okay, see this here, you can see a plano convex lens. It's a part of a sphere. Okay, plano convex lens is a part of a sphere of which lens is a part, right? So what you are estimating? You are estimating the radius of curvature of the plano convex lens. Here you have a glass plate. So between the plano convex lens and the glass plate there is air. What is T here? Thickness of the air film, correct? So what is R here? Radius of the plano convex lens, right? Okay, now okay, now with this geometry, one can estimate radius of curvature of the plano convex lens. You know, around the point of contact, thickness of the air film is uniform, no? So as a result, you are getting bright and dark rings. So the diameter of dark rings, you are getting both the dark as well as bright. Diameter of dark ring is directly proportional to square root of natural number. Diameter of bright ring directly proportional to square root of odd natural number. So since diameter of dark is directly proportional to square root of natural number, I use that condition. With that condition, I calculate radius of curvature of the plano convex lens. So what is D here? Diameter of m plus nth dark ring. This is Dn is diameter of nth dark ring. What is m here? M is the difference between n plus m minus n gives you m. What is lambda here? Wavelength of light source used, correct? So remember, to derive this relation, what is the condition used? Diameter of darkening, this is D. Diameter of darkening is directly proportional to square root of natural number. So you are seeing the ring pattern in the reflected system. So light you are getting reflected from the bottom, no? Right? From here. This is a reflected system, right? So you are seeing the ring system in the reflected system, right? If you see the ring system somewhere here, we say that one is transmitted system. So the ring system, what you see here is reflected, here it is transmitted. So both are complementary in nature, meaning, so reflected system, at the point of contact there is darkness, dark ring. Transmitted system, at the point of contact there is bright ring, correct? So the ring system, both the ring systems are complementary in nature, right? Now you just see here right side you can see a diagram now. So what you can see is ring system. At the point of contact, thickness of the air film is 0, hence there is darkening at the point of contact. This is 0th ring, this is first ring, second ring, third ring, so on, right? With the help of crosswire, imagine you have a crosswire here. This crosswire, you can move either left or right. So on either side of the crosswire, the rings are symmetrical, right? Then you can see here the diameter, the diameter of bright and dark rings are different. You know, diameter of dark ring, this is dark ring now. Diameter of dark ring is directly proportional to square root of natural number. Bright ring directly proportional to square root of odd natural number. So you can see even the thickness of these rings keep on decreasing, no? Because of the, you know, why? It's because of the refractive index. So you know, there is between the plano convex lens and the glass plate, there is air, no? There is air, right? So if you change the medium, right, the thickness also change. The thickness also change. So the variation of fringe width is because of the refractive. It depends on the refractive index of the surrounding medium, right? Okay, now we shall move. Right, now you see here, for working now you require a traveling microscope. This traveling microscope, it moves along one direction. This is one dimensional traveling microscope, right? And here you can see head scale, and here you can see pitch scale. This is called pitch scale, and this is eyepiece. This is eyepiece. This is rack and pinion screw. Now you can see two screws here. Now these two screws we use for focusing, right? So this one, screw number 1, screw number 2, these two we use for focusing, and here you can see the reflector, right? Okay, now we shall move further. Right, now I said there are two scales now. Okay, one is the rotating scale, head scale, and horizontal scale we say this is pitch scale, this is head scale. Okay, this right hand side, you know, what you say is a pitch scale, right? Pitch scale. If you look at this pitch scale now, see, just look at this. This is 30 and 40. Between 30 and 40 there are 10 divisions, right? So on pitch scale you can see 10 divisions in between that is in 10 mm between this 30 and 40. You can see here how many divisions are there. 10 divisions are there. Value of one division is 1 mm, right? Value of one division is 1 mm. We'll move further. Okay, this is the side screw, right? Just see this. This is okay, right? I'm sorry. Okay, this is the head screw, right? This is the head screw on which there are 100 divisions. On this screw now there are 100 divisions, right? Remember pitch scale, here one division is 1 mm. Here there are 100 divisions on head scale, right? Okay, now you see here, this is also the side view. You can see the rings, you can see the divisions very clearly here, right? But this is 0, right? And this is 100, correct now? Right, 100, right? So how do you count this? This is okay, 90, let's say this is 97, 98, 99. Okay, so now here between 0 and 90, correct now? So now you can see this reference line, it is between 98 and 97, correct now? Okay, now remember there are 100 divisions on the head scale. Okay, now how to calculate the least count of this instrument? To understand, to calculate the least count, what is least count? It's the least measurement that you can make with any instrument, right? So this is the least measurement that you can make. How do you calculate least count? With the formula pitch by total number of head scale divisions. Pitch by total number of head scale division. What is pitch? So pitch meaning, you know, this is the head of the screw, correct now? If you rotate head of the screw by, imagine you give one complete rotation to this. For every one rotation, this PSR move by 1 mm. If you give two rotations to this will move by 2 mm. That is distance moved on pitch scale by number of rotation given to head scale gives you pitch, right? So we are using 1 mm pitch. That is, for every one rotation, the pitch scale move by 1 mm. Pitch is 1 mm. There are 100 head scale deviation. HSD meaning head scale deviation. 1 by 100 gives you 0.01. So 0.01 mm is the least count for the traveling microscope, right? So after you learn how to calculate least count, then we must know how to calculate the total reading. How to calculate total reading? TR meaning total reading, PSR means pitch scale reading, HSR head scale reading, LC least count. So LC first you calculate how much did you get? 0.01 mm, right? So then what you do? Focus this TM on the ring system. This is where there is plano convex lens and the glass plate. When you focus, you get the concentric rings, no, Newton's rings, right? So then after focusing one by one, imagine this is a imagine ring number 2. You have to place the crosswire like this, right? And note down the reading. So where you should take the reading? Here. So note down PSR here and HSR here. How to calculate PSR? See this 0th division. This is the reference. So imagine this reference is between, let's say, 28 and 29. So here 28, it's between 28 and 29. What is the lower value? 28 mm. So 28 mm is the PSR. Then you see here. Then you see the head scale. See this part. You can see the reference line here now. This reference line is between 97 and 98. What is the lower value? 97. So 97 becomes your HSR. So with this, I'm getting total reading as 28.97 mm. So in this way, I can take the total reading with the help of this microscope. Now, to move the crosswire now from one direction to other direction, you need to rotate this head of the screw. So depending on whether you move clockwise or anti-clockwise, the direction of crosswire change. Remember, to move, you should rotate this crosswire. You should rotate the head of the screw, right? Further. Okay, now, right. Now you see, this is how the ring system look like. So here there is a darkening at the point of contact. Then this is the 0th ring. Then first ring, second ring, so on. Correct now. So we are using sodium light, no, yellow light. So hence this is how the ring system look like, right? Okay. So you cannot use polychromatic source, because if you use polychromatic source, different wavelength, polychromatic source contains different wavelength. As a superposed, no, you cannot see the bright and dark fringe boundary. You cannot see very clearly because of the distortion. So distortion happen if I use a polychromatic source. So monochromatic source, you can see the boundary very clearly, right? There is no distortion, right? We'll move. Okay. Now you see here, you can see the ring system here. Okay, so left hand side you can see a video now that will play now. So with this video, what you see is here inside this you can see a ring system. So somewhere towards left side there is a crosswire, right? So you can see as you rotate the head of the screw, how the crosswire move, that you can understand with the help of this video, right? Let me move further. Okay, now you see here. Now, okay, now this is the table that you are using. Look at this. The first column you have a ring number, right? Then what you have this TM means traveling microscope. Reading you measure in mm, right? So LM, that is left hand side reading. RM, right hand side reading. Difference gives you diameter, LM difference RM. Then if you know dm, calculate d square m, unit mm square. Then we shall name few rings as n number, right? Then ln, that is left side reading, rn right side reading. Then ln difference rn gives you diameter of nth ring. Then square it, you get d square m. D square m minus d square m is the difference between dm and dn measured in mm square, right? So what you do, after you get the ring system, right? Imagine this is the center of the ring system, right? So you have to move. This is the left of the crossbar, this is right of the crossbar, correct? Right of the crossbar. what you do, you have to move crosswire towards left, go near outer edge of the outer edge of 12th dark ring. So imagine this is 12th dark ring, right? So the crosswire is almost at the uh, outer edge of the 12th dark ring. Then what you do, note down PSR HSR. You can see here PSR is 46 mm, HSR is 1, so finally you get 46.01. Then from a 12th ring you should move to 10th dark ring, right? So you are moving from 12 left to 12 right in one direction. Okay, so after 12th ring, next what you do, move to 10th ring. So to 10th ring, you can see here I'm getting how much, 45.79. so the value keep on decreasing. You are moving from left to right, but the you are moving the crossword from left to right, but the scale move from right to left. As a result, total reading keep on decreasing. What you see is real and inverted image now. So after eighth ring, what you do, okay, next you tabulate the readings here. Okay, okay. Now you see here, okay, sorry, here you see this. Now sixth ring, here you note down. Then fourth ring 44.91. Then second here 44.52. So after second ring on left hand side, then what you do, cross the center, then move to second ring on right hand side. Okay, so 41.95, then 41.59, then 41.20. Next what you do, move here. Okay, this is a eighth ring, right hand side. Then 10th ring 40.69, 40.45. Then knowing these two, now calculate the difference is 5.56, square it, you get 30.91. So similarly complete all this. So on for m rings, then same for n rings also. Okay, now you see here for n rings also you finished. Then finally last column you just see d square m minus d square m. I'm getting 14.67, 14.98, so on. Then calculate the average. With that average, one can estimate the radius of curvature of plane lens. Now we should move further. Okay, right, now you see here the average value of d square m minus d square m from the table is 14.73 mm square, that is 14.73 10 power minus 6 meter square, right? So what is the ring number? The difference is m minus n, it's around 6, right? Then how do you estimate radius of curvature? With this formula, d square m minus d square n by 4 times m minus n into lambda, right? Then you know value of d square m minus d square n is 14.73 and m minus n is 6 and lambda is 5893. With this you get radius of curvature around 1.04 meter, right? Okay, now what are the application of this experiment? Number one, you can estimate the refractive index of surrounding medium, meaning, right? So imagine this is a plano convex lens and this is glass plate, right? Between the two there is air, no? You can calculate the refractive index of the medium surrounding the plano convex lens and the glass plate. Okay, next you can estimate the unknown wavelength of a monochromatic source. So instead of sodium source, imagine some other source you are using. So with the help of Newton's rings, I can estimate, if you know the R value, no, right? R value of a standard plano convex lens, right? Knowing d square minus d square n, m minus n, I can calculate. Look at this equation I use, right? This equation. So here I'm estimating lambda naught. So if I know R value and I calculate d square minus d square n, with this I can calculate the wavelength of the unknown spectral line, right? And then I can check the optical flatness. Below the plano convex lens there is a glass plate. Now if it is not uniform, if the surface is not uniform, then the thickness of the, just see, this is one of the circle. Now the thickness of this circle or the rings, it won't be uniform if if the glass plate is not optically flat, right? What I can do, for imagine it is not optically flat, okay, you see the ring pattern, then what you do, take out the glass plate, polish, right, n number of times till the thickness of the plane, thickness of the neutron rings is almost uniform, right? Any ring you can count. Let's say second ring or fourth ring, any ring as a reference you take, and by studying this, one can check the optical flatness of the glass plate. With this, we conclude. Thank you very much.